Good day everyone, we are from Hackathon Warriors. So today we are going to present about our project with the title of the Distillation Column Efficiency Analyzer. Our team consists of IMRAN NAZMI, JAUHAR and me, AFIFAH DAYANA. Our application focuses on replacing tedious manual engineering methods with a modernized automated approach to column performance evaluation. In industrial operations, manual analysis is a major bottleneck. Traditional methods rely heavily on discrete, disconnected experimental data points that require time-consuming manual interpolation and step drawing, leaving a high margin of human error. Our automated standard addresses this by instantly generating continuous mathematical curves and using algorithmic iteration to provide exact analytical convergence through an error-free diagnostic dashboard. To continue, this slide illustrates the core architecture of our system. It begins with data ingestion, where raw operational inputs like tray counts and VLE data are streamed into the system. Next, the MATLAB Art Designer engine serves as the central computation core to process numerical iterations instantly. Finally, it produces the engineering output, delivering definitive efficiency percentages and actionable maintenance recommendations in real time. To understand what happens under the hood, raw data travels through a 5-step sequential pipeline. We begin with the raw input data, which passes into a regression engine to feed a continuous model. From there, a root finding algorithm solves for effective relative volatility. The system then applies the Fransky and efficiency equations during the engineering evaluation stage, automatically rendering the final diagnostic dashboard and MATLAB tile diagram. Here is the visualization of our curve fitting solution. Accurate MATLAB tile analysis requires a continuous equilibrium curve, but physical experiments only give us the discrete points seen on the left. By implementing a high-order polynomial regression engine, our code automatically fits this point into a smooth, reliable curve, completely eliminating the need for manual interpolation. Ultimately, our numerical processing is governed by classical chemical engineering thermodynamics. The system calculates relative volatility, alpha, to establish the ease of separation, uses the Fransky equation to determine the absolute minimum theoretical stages required, and finishes by evaluating the overall tray efficiency, E0. This benchmarks the real-world performance of the column against theoretical perfections, giving plant operators immediate actionable data. Ultimately, our numerical processing is governed by classical chemical engineering thermodynamics. The system calculates relative volatility, alpha, to establish the ease of separation, uses the Fransky equation to determine the absolute minimum theoretical stages required, and finishes by evaluating the overall tray efficiency, E0. This benchmarks the real-world performance of the column against theoretical perfections, giving plant operators immediate actionable data.
For the app development, we implemented the seamless parameter ingestion via an intuitive graphical interface. For the operational input panel, the hardware bounds establishes the physical constraint of the plant, the operational targets define the precise binary separation parameters, and the data import allow bulk injection of raw thermodynamic data. For the diagnostic dashboard output panel, we implemented an instantaneous diagnostic output and engineering recommendations. For example, the MATLAB tail diagram, the generated diagram, does a polynomial regression to successfully fit a continuous blue VLE curve, allowing the algorithmic stage stepping to find exactly 10 theoretical edges. And then it calculates the tray efficiency. The application automatically divides the theoretical stage, which is 10, by the actual trace, which is 15. And then it shows us an actionable status. For example, in this one, the system verifies the performance is acceptable and then recommends maintaining the current reflux ratio, which is 2.5. Now for the live demonstration of the app. When I first open the app, it have a set amount that is shown in this operational input side that will load and then give us the graph, and then the actual tray number will be calculated to calculate the tray efficiency, which will show here, which is 636.67, which is above 60%, so the status will show us that the column performance is acceptable, and the recommendation will show us that to maintain the column refract ratio in the monitoring cycle. If we decide to use other data, such as I have an example here, and we can see in the Excel data that we have the different sets of data here. We can use this data to upload it into our app through the import Excel point, and then we can click it, and then we can select the data extract, and then we can open. After we successfully import, we can press OK, and then the data will be here. After we know the data here, we can press the diagnose column system, and then it will show us from the curve using the new data, and then it will plot the new McCabe stepping stages for the new curve. After using the new curve and the refract ratio same as before, it will produce that we calculate the stages of 8, and we use the actual trade as same as before, 15. And it will show that the calculated efficiency is 53.33, which is below than 60%, which will cause the status to show that it is trail falling happening, or weeping happening, or flooding is suspected. And the recommendation will show us to schedule the immediate column turnaround and inspect the feed tray. As we can see in the diagnostic dashboard import, all are complete, and also the information input is all fit. If we fail to input one of the operational data, it will not show us the answers. That's all from me.
This slide shows how optimizing the theoretical stages of a distillation column can contribute not only to process efficiency but also to planetary sustainability. Starting from the center of the diagram, the first step is trait efficiency detection. Our application continuously monitors the column and can quickly identify when the actual trait performance falls below the optimal efficiency. This gives engineers an early warning before the problem becomes more serious. Once inefficiencies are detected, the next step is targeted reflux optimization. Instead of relying on trial and error or operating with excessive safety margins, engineers can use real-time data to adjust the reflux ratio more precisely. This helps maintain the desired product purity while avoiding unnecessary overprocessing. The final outcome is massive energy reduction. Distillation is one of the most energy-intensive operations in the chemical industry, accounting for approximately 50% of the plant's operating costs. By optimizing the number of effective theoretical stages and preventing inefficient reboiler and condenser operation, the column requires less heating and cooling energy. This reduction in energy consumption directly translates into lower greenhouse gas emissions, reduced fuel usage, and better conservation of natural resources. In other words, improving column efficiency doesn't just benefit the plant economically, it also supports global sustainability goals by reducing the environmental footprint of industrial operations. Overall, our application demonstrates how a simple improvement in monitoring optimization can create a ripple effect, leading from better trade performance to lower energy consumption and ultimately a more sustainable chemical process. Beyond improving process efficiency, our application also delivers significant environmental benefits that support sustainable industrial operations. First, it helps achieve a drastic reduction in greenhouse gas emissions. By optimizing the distillation column and maintaining efficient operation, the system reduces the amount of steam reduction from fossil fuel-powered boilers. This lowers fuel consumption and directly reduces carbon dioxide emissions. Second, the application promotes waste reduction and material conservation. By providing early warnings when product quality begins to drift off specification, operators can take corrective action before large quantities of materials are wasted. This minimizes the need for energy-intensive redistillation and reduces chemical waste. Third, it contributes to the prevention of environmental hazards. Because the system continuously monitors the column, it can detect abnormal operating conditions early. This reduces the risk of equipment failure, toxic chemical leaks, and emergency flaring, making the plant safer for both workers and the surrounding environment. Another important benefit is thermal pollution mitigation. Optimizing the reflux ratio reduces unnecessary cooling water usage, which helps limit hot water discharge into nearby rivers or lakes. This protects aquatic ecosystems and supports responsible water management. Finally, the application helps extend equipment lifespan. Predictive maintenance recommendations allow operators to address fouling or corrosion before major damage occurs. As a result, equipment lasts longer, maintenance costs are reduced, and fewer replacement parts need to be manufactured, lowering the overall carbon footprint. Overall, these environmental benefits align closely with the United Nations Sustainable Development Goals, particularly SDG 9, Industry, Innovation and Infrastructure, by promoting smarter industrial technologies, and SDG 12, Responsible Consumption and Production, by improving resources efficiency, reducing waste, and supporting more sustainable manufacturing practices. That's all from us. Thank you.